In this video, we'll take a look at how temperature and body size are related. So remember that larger animals have more cells, and that because the cells of animals are all about the same length for the same kind of cell, the same size, you can predict that cell number is going to go up as exactly as fast as does organismal mass. Volume too, because animals are all of the same density, is going to go up 1-to-1 with an increase in mass. This is a log-log scale. Notice too that as that slope is 1, that even though surface area gets bigger as animals become heavier, get bigger, the slope of that line, the slope of that relationship isn't as steep. So although surface area gets bigger as animals get bigger, it doesn't do so as quickly as does volume, and therefore the bigger the animal, the lower the surface area to volume ratio. The first consequence of this relationship between animal size and the surface area to volume relationship of the animal one consequence, heat is made by cells. The number of cells is a rough indicator of how much heat is made. Heat is exchanged, on the other hand, from the surface of the organism. Not every cell is at the surface, therefore not every cell is exchanging heat with the environment. And so we see that surface area is the feature of the animal's geometry that dictates how fast temperature exchange with the environment can occur, but heat generation is more a function of volume. The consequence of that is you don't have very small endotherms. Temperature regulation isn't possible if you're a very small animal. You don't make enough heat to make up for the rapidity with which the environmental temperature influences your body temperature. One of my favorite papers talks about how fruit fly larvae adjust their metabolic rate by migrating to the perfect temperature. So normal fruit flies have a temperature that they will actively seek out that's around 22 degrees centigrade. You can see this temperature as this location on this part of the figure. So these are strips, and every line, hard to see there, but there are a series of lines, and every one of those lines represents a gap, and in between those lines you have very, very tightly controlled temperature. So it goes from cooler to warmer. And all of the wild type animals gather around the 22 degree temperature. Now, there's a mutant whose ability to control its metabolism is missing, is defective. This animal has a much faster than normal metabolic rate at the same temperature. Consequently, the larvae of this animal seek out cooler temperatures. So the average temperature that this larva will inhabit, given the choice, is around 18 degrees. These animals essentially become 18 degrees internally. At 18 degrees, their metabolism is moved to a slower rate, a rate like that of the wild type animal. What about the size of bigger animals? So what about animals that are big enough to be temperature regulators? Well, most very big animals are temperature regulators. There are some gray area animals. Sharks, for instance, are warmer than the water around them, but they're still not endotherms. They're still not regulating temperature. They're just making so much heat that they consequently make more heat than they lose to the surrounding water. Most large animals, I said, are temperature regulating. And when you think large animals, I imagine many of you think dinosaurs. And many of you may know that there is a great controversy, or has been until recently, a great controversy as to whether dinosaurs were so-called cold-blooded animals, in other words, temperature conformers, or warm-blooded animals, temperature regulators. So, really strong evidence has been published in the last few years regarding this, and one piece of that evidence is that of the ichthyosaur. Now, this looks like a fish, but it isn't. It's, I guess it looks like a marine mammal, but it isn't. This is a dinosaur. And this dinosaur has been well enough preserved that the molecular structure of its bones are revealed, I guess, in the fossil remains. And by looking at these, one can pretty definitively say the temperature at which these bones developed. And what you'll notice, and I think it's teeth specifically in this experiment, the teeth of this animal reveal that even though it has been found in waters that we know had a variety of different temperatures, so this ichthyosaur was found in a variety of different places, no matter what temperature water the remains of these animals are found in, it becomes clear that they had a 37, 38 degree body temperature in all of those different temperature waters. Dinosaurs were temperature regulating animals. Generally speaking, temperature regulating animals maintain a temperature around 100 degrees Fahrenheit. The range is pretty small. It runs from maybe down as low as 96 up to 104 degrees. A very narrow range. The temperature of an animal is not, if it's a temperature regulating animal, is not varied by animal size. It's not varying by animal location. So animals that live in colder environments do not maintain a lower body temperature. All of these animals that you see, I stole this from an integrative physiology textbook, all of these animals have essentially the same body temperature. Now, this picture might lead you to believe that they all have the same basal metabolic rate, but they don't. The basal metabolic rate has been normalized so that all of these animals can compare. So it's been set to 1 for all animals. And you can see that the insulation quality of these animals differs very significantly, but their body temperature remains the same. And you can see that these animals come from a variety of biomes, different temperature environments, and that there are a variety of sizes. Why this 37 degree body temperature is a mystery. There is a prevalently discussed hypothesis out there that 37 degrees provides a very nice temperature trade-off between not being too fast. Any faster a body temperature, and it's postulated we would have to eat too much. Chemical reactions would go too fast. We'd burn too much fuel. And too low a body temperature. At a lower body temperature, chemistry happens more slowly. It's harder to do work. But some people think that the key is many, many things that might otherwise be pathogens can't live at a body temperature as high as 37 degrees. Of course, E. coli and the things that do attack us have evolved to attack us and can manage that temperature quite nicely, thank you. But many, many more types of bacteria, and especially fungus, that might otherwise be pathogens, don't function at that temperature. So there's one hypothesis for why 37 degrees. There's some other features relating body temperature to size. I'll show you first a picture of fruit flies that have grown up at a series of temperatures, 17 degrees, 25 degrees, and 28. Now, that y-axis is body size. And you'll notice that that temperature conforming animals that grow up in cold temperatures tend to be larger. That's strange because they grow more slowly. The explanation is, although they grow more slowly, they mature even more slowly. So the rate of maturation, the rate of aging in a way, becoming sexually mature, becoming mature enough so that growth is no longer part of the program, is affected even more by temperature than growth rate. So for maybe 85% of temperature conforming animals, larger individuals form at colder temperatures. What about temperature regulating animals? Well, this has been a very hotly debated issue as well. Bergmann's rule states that for any given type of animal, say canines or horse-like animals or apes, the average size of animals increases with distance from the equator and presumably with lower temperature. So this has been in disrepute to a certain extent, but the most recent data seems to confirm that even humans, even within one species, there is a trend that living in a colder environment leads to bigger individuals. The top left panel there shows you that the body mass of animals living at closer to the equator is lower than those living further away. So this graph supports Bergmann's rule that animals tend to be larger if they live in colder environments. And this figure supports Allen's rule, which states that animals tend to have a shape with a lower surface area to volume ratio when they live in a colder environment. You can get a lower surface area to volume ratio by having shorter limbs, a more columnar trunk. The length is reduced so that the relative surface area is reduced. You can think about making up a Lego structure, and the more square it is, the lower the surface area to volume ratio with respect to something that was, say, taller and flatter.